Okay, great. Okay, I'm back. Thanks, guys. Yeah. Woo! Yeah, I also work on Perseverance on the SuperCam instrument. And so the main things that I'm really interested in are just, I want to find signs of past life in rocks. I'm really interested in listening to the sounds that we can hear on Mars. We actually have a microphone on SuperCam. And I really enjoy going into the field and testing new techniques. And this is just a picture of me in the Canadian Arctic. Several people here were with me. This is the biggest selenite crystal I have ever seen in my life, just sticking out of the ground. It was amazing. So you know where I am now, but how did I get here? Well, in 1986, I was 7 years old, and I got to see Halley's Comet. You may know that this is a short period comet that comes around every, I think, 76 years. So it's one of the only objects that you can see that will come back in a human lifetime. So I saw this, and I was like, oh my gosh, like the sky is not a dome. It's actually three-dimensional, right? There's stuff out there, and we don't know what's out there, actually. So that got me hooked. And because of that experience, I ended up majoring in astronomy as an undergraduate. I went to Smith College, so if anyone's looking, any women out there looking to go to an amazing women's college, I would recommend Smith. But after I finished my degree, I still wasn't sure what I wanted to do. And so I had a mentor who said, Nina, why don't you sit down and think about what is it that you love to learn about, even when no one makes you do it? So I was like, all right. So I sat down with a pencil and a piece of paper. And this is my real list. This is a real list. I was like, okay, well, I love science fiction. I love reading about what-if questions. And I really like spaceships because they're awesome, and aliens. So obviously, I should be studying Mars, right? This all adds up. So at that point, I called up a planetary scientist at Los Alamos. We heard about him before, this Bill Feldman, who is a pioneer in the field of neutron and gamma ray spectroscopy. I called him up every day for 2 weeks. I left messages. Sometimes he would answer. He's like, I can't talk now. But I kept calling. Finally, he was like, what do you want? And I was like, hey, can I have a job? And he's like, yes, stop calling me. So that's how I started my career. But then I realized that if you wanted to study a planet that's made out of rocks, you need to know something about rocks. So I ended up going to grad school in geology. So I got my master's degree at Wesleyan University in Connecticut. And then I came back to New Mexico to work, to get my PhD at UNM. And I was there when Chip was there. Chip's still there. And that's how I got to where I am now. So the idea that there was life on Mars is actually not a new one at all. I want to direct your attention to these absolutely real New York Times headlines, okay? So the one on the left is from 1906. It's quite definitive. There is life on the planet Mars. That's it. We did it. 1906. What am I doing? And this was based on telescopic observations made by Percival Lowell in Arizona. And so he kept making these observations. He really thought he saw large construction projects, and specifically canals that were connecting bodies of water from one place to another, and developed a whole hypothesis that this was a civilization about to be on the brink of extinction, and they were trying to save themselves. And you can see he reported again in 1911 that the Martians had actually built 2 new immense canals in 2 years. So that's pretty impressive, right? So we now know, of course, that probably wasn't the case. But we couldn't know for sure until we went. So people were very excited when, in the 70s, we sent landers to the surface of Mars for the very first time. And everyone was really disappointed. They're like, it's just a bunch of rocks and dirt, you guys. Like, where are the cities, right? Even though we were pretty sure there weren't cities, it was still kind of a crushing blow emotionally. And this led to about a 20-year period of no more Mars missions. Everyone's like, that's just a bunch of dirt. Of course, as a geologist, I'm going to tell you that rocks are actually pretty interesting, and they can tell you a lot. But everyone was just needed to get over the disappointment. So things started to look up for Mars research in 1996 when a meteorite from Mars was identified. It was one that was found in Antarctica, and someone thought they saw something that looked like a microbe or minerals made by microbes. And if you were alive then, you might have remembered that then President Clinton made an incredible announcement. And he said, today the very romantically named Rock 84001, speaks of the possibility of life. If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered. And I think that's true. I would stand by that. Now, after that announcement, scientists were like, whoa, like, I don't know if this is actually life. This doesn't seem like enough evidence. But what would be enough evidence? And this spawned an entire new field of study that's called astrobiology or exobiology, the study of what life might look like not from Earth. So I'm grateful to this rock because that's why we have jobs now. So you might wonder, why do we even care if there are Martians or were Martians in the past? Why does it even matter? And I would argue that it's because that addresses two incredibly important and fundamental questions. The first one is, are we alone? Are we the only life in the universe? Are we unique? Are we special in any way? Now, if you heard John Grunsfeld speak yesterday, you'll know that, people think that they're very special. We all think that humanity is very special, but history has shown us time and time again that we're a lot less special than we often think we are. And the other question that we want to answer is, where did we come from? How did we arise? How does life develop? And how conducive to life is Earth, actually? We think of Earth as this ideal place for life, but there's no reason for us to believe that. We don't know anything about life. We know that life exists here. We don't know if there might be better places for life to exist than Earth. So these are really fundamentally important questions. And what's so lucky for us is that we have our nearest neighbor, Mars. We can test a lot of hypotheses that will help us understand the answers to these questions by doing research on Martian rocks. And that's because Mars is the most Earth-like of all of our neighbors in the solar system. And in fact, we have very similar formation histories, right? We formed in the same solar system, really close to each other, out of very, very similar materials. So we have an opportunity to test hypotheses on another planet that also formed near us. So from all of our missions to Mars, and there have been many, we know that Mars was certainly a habitable place. And what do I mean by habitable? That's an environment in which life as we currently understand it could exist. But what we don't know is if it was ever inhabited. Was life ever there? But what's interesting is that, we know that Mars was habitable not just in the present, but actually at the right time. So I'm showing these two geologic timescales for Earth on the top and Mars on the bottom. These are very approximate. So right at the start, we have some evidence from Earth rocks that show that life arose very early, relatively early in Earth's history. And this just happens to be right around the time of where the rocks that we're studying on Mars, this is when those rocks were forming. I just want to point something out here. So if you look, if you went outside and just pulled a rock from somewhere, it's probably not that old. It's probably not even more than 1 million years old. I mean, that's pretty old for people, but it's not that old for Earth. And that's because Earth has a really dynamic surface environment. So it's constantly recycling and reshaping materials. Now, in contrast, Mars is more like a rock museum. Rocks, the surface was very dynamic billions of years ago, but it hasn't been as dynamic since. And so we have a window into a period of time that we've lost on Earth. And these environments on Mars were absolutely habitable. We can see that there were lakes, long-lasting lakes of fresh water that had all the ingredients that life would have needed. And we can see these environments preserved in a way that we have lost on Earth. So really, we need to take a look. We can take a look at these rocks on Mars. We can learn something about not only the history of Mars and life on Mars, but also how life on Earth might actually have arisen. And we have more information now from studying Mars than we would have if we only studied Earth. So how do we do this? How do we use rocks to see if there was ever life? And there's several lines of evidence that we can use to find these so-called biosignatures. Of course, an obvious one are organic molecules. We're bags of organic molecules here. But we can also look for minerals that are formed by life. life actually is very good at making many types of minerals. We're all walking around with some minerals. Our bones are made of something called apatite, so we actually grew some minerals, and those persist after we are no longer alive. So somebody can see that ages hence that we existed. We can also look for structures and textures. Some of them are macroscopic, a large scale. Some of them are microscopic. So like a macroscopic structure you might look for is a dinosaur bone sticking out of a rock. That would be a good one. This is also, I'm showing a picture here of a stromatolite. That's a microbial mat. That's some of the most ancient life on Earth. We can find fossilized stromatolites. We can also see individual cells fossilized. We can see that in rocks. Those structures can be preserved even though the soft tissues are long gone. Of course, we can look to chemistry as well. We know that life requires certain elements to form. We need to see all of those elements around if we're going to say that there's going to be life there. So my favorite organic, or the most, I would say, common elements that life uses are the chinops. Some people say schnapps. That's a little spicier. But that's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the building blocks for those organic molecules. So we need to see those there. And then finally, we can look for isotopic ratios. You may have heard of carbon dating. So this is a way that we can use the ratio of different carbon isotopes to understand when something was alive and how old it was. So you need all of these things. This is actually a lot, one of these lines of evidence would be amazing, but is not enough. You're going to need multiple lines of evidence. And a lot of these things are really hard to assess with spacecraft instruments. I can tell you, we're trying. It's hard to do. So if you can bring these samples back to your laboratory, you have an opportunity to do a lot more measurements than you could otherwise do. And you can also, as Chip was mentioning, save samples for future analyses. This is really important. We don't know what techniques we might develop in the future. We might have more knowledge that could lead us down a different measurement path. So it's really important. If we have samples in our hands, we can actually do a lot more with them and learn more. I want to just pause here and just talk a little bit about the search for life and draw a distinction between looking for life in the past and looking for life in the present. Because it really changes where we look for it and how we look for it. So where is it? What do we do to find it? So the current search on Mars is focused on ancient life. So what are the traces that life leaves behind, and where do they leave them? How does it change over time? These rocks, as I mentioned, are billions of years old, so they've seen some things, and they won't be exactly the same as if they were fresh. So we also know that Mars is less habitable today than it has been in the past. So we can't base our search on today's environment. We have to think back, what was it like then? And we have to ask, so that we'd have to ask different questions about present day life. You'd have to say, well, where are the present day oases, right? Where could life exist today? That's not going to be the same as where life could exist 3 billion years ago. Because you need to have conditions that were a lot more hospitable to, in the present day than they are in the general surface. So this is why right now the search for life on Mars is focused on ancient life. Okay, I know it's Saturday, all right, but I want you to bear with me, because this is a really important part of our search for life and how we can actually do this. And I'm going to tell you, it's redox chemistry. I know, you could take a little nap if you want. The take-home point is at the bottom, but just bear with me here. What is redox chemistry? I'm so glad you asked. That is short for reduction and oxidation. And what that means is that some elements can give or take electrons. So if you're an oxidized element, you've lost an electron. You gave it to someone. If you're reduced, you got an extra one. That's so great. To do that requires energy. So a great source of energy for life is light. Photosynthesis is a classic redox chemistry scenario. So you use light, plants use light, and they turn it into sugar, basically, and then they can continue to live. Microbes can also use other reactive oxygen species to do this type of chemistry. But what's so interesting about redox chemistry is that it's very sensitive to environmental conditions. So if you know something about the redox state of these elements, then you know something about the environment in which they formed, in which they formed minerals that we can see today. Now, some elements have multiple redox states, and that's actually pretty useful. So iron's the classic one. When you see an oxidized iron, that's rust. That's it's lost an electron. And then if there's a lot of iron that's kind of gray, that is reduced iron. And so what that means is that it changes the types of bonds that that element can have. It can have more than, it could have multiple possibilities for bonds depending on the redox state. So here's an example. If you have one iron and one oxygen, because you have reduced iron, that's a mineral called wustite. If you have more spaces on that iron because it's oxidized, you can have 2 irons, 3 oxygens, and that's hematite, totally different mineral, forming in a different environment. So that's exciting because now that's something that can last billions of years, right? The redox state determines the bond. The bond, how elements are arranged, that's mineralogy. And then that tells us about the environment 3 billion years ago. And also, microbes are experts at producing these redox disequilibria, meaning it's not going to go to that equilibrium spot. It's going to form redox bonds that are just the redox states that are not expected given the other chemistry around it. And that can be a big indicator that there were microbes there. See, redox chemistry, it's awesome. So let's bring it back. Let's zoom out now to our Mars rover family. What do we have on Mars where we can make these kinds of measurements? So these are all mock-ups at the Jet Propulsion Laboratory in California of all of the Mars rovers that we've ever sent. These are 2 full-size engineers for scale. You can see we started with a very small rover, the little Sojourner rover that was part of the Pathfinder mission in 1996. That was mostly just to say, hey, can we make a rover that works? Yeah, we can. So then in 2003, we launched twin rovers. You might be familiar with them, Spirit and Opportunity. And they landed on different sides of the planet to do 2 different types of investigations at the same time. There is actually a film going to be shown, I think it's tonight, Good Night, Oppie, which is about opportunity. So it's a heart-rending movie, but I really recommend it. It's very touching. And so then in 2011, we launched the absolutely massive Curiosity rover. And Curiosity's official name is actually the Mars Science Laboratory because it was like sending an entire laboratory to Mars. And so we're still going. A lot of people think that we died, but we are still going. It's almost 13 years. But not content to rest on our laurels, we launched a twin of Curiosity in 2020 called Perseverance. Its official name is Mars 2020, a little less creative there, but that's because it launched in 2020. It too is still operating on the surface of Mars in a different place. So I'm mostly going to tell you results from both of these missions. These are the ones that I work on. So let me just tell you a little bit more about the goals of Curiosity. So the goal of Curiosity was to assess the past and present habitability of the Martian environment. So remember, habitability is not finding life, but rather places where life could exist, life as we know it. So we're looking for these past environments that have things like water and organic materials, building blocks. We also want to understand just the basic geology for science and understand climate on Mars and how it's changed over time. We just want to understand, what are the surface processes that have led to the surface that we see today. And of course, we want to prepare for human beings to go there. And so humans are very picky about their environmental conditions. They like very specific temperatures. They don't like radiation very much. So we are assessing those factors as well. So again, this has been going. I said 12 Earth years. That's true. It'll be 13 years in August. So we have a ton of information from this mission. So this is a topographic map, really an elevation map of Mars. So red, the warmer colors are higher elevation, cooler colors are lower elevation. You might notice that there's a really low part in the north of Mars. I'm not going to talk about that, but if you have questions, we can talk about it after. So we've landed over here in this box, this reddish pink box. That's Gale Crater. That's where Curiosity is. And it's right on the edge of this dichotomy between this very rough southern part and the smooth lower part. So it encompasses a lot of geologic time. So you might have seen in the news, maybe, I don't know. I'm still getting notifications about this. It's like in my news feed. We found something really weird, unexpected. We found elemental sulfur, and that's not the element sulfur, it's elemental sulfur. So we drove over a rock, and because the rover is kind of big, it crushed the rock, and we looked back, and I don't know if you can really see this, but it's weird. It's yellow. There's like weird yellow stuff in there, and we were really surprised. That is not what we expected. So then we had to, shoot it with our laser and figure out what it was made out of, and it's just sulfur. It's all sulfur, and it turns out that we are in a province. You can kind of see that on this side. There's just a bunch of rocks that look kind of white on the outside, and they're all just sulfur, native sulfur. I mean, that's a huge, huge amount of sulfur, and super weird and unexpected. So what is this even? So let's go back to redox, okay? How did we get this redox state of sulfur? Because it's right in the middle. So the surface of Mars is pretty oxidized. And so the oxidized form of sulfur is really abundant on the Martian surface. This is a sulfate mineral. We see it everywhere. We see it every day. It's great. Still very interesting. We also know that there is reduced sulfur. We've seen them mostly in meteorites and a little bit on Mars. It's not very common, okay? It's much more common to see oxidized sulfur, just given the environmental conditions. Well, this is right here in the middle. This is just sulfur, and it's not stuck to anything else. It's super weird. And it's out of equilibrium with the surrounding environment. So there's a little flag there. That's interesting. How did that happen? We can look to Earth for some information. So there are multiple mechanisms for elemental sulfur to form on Earth. Volcanoes are a big one. You could add organic material to some of your oxidized sulfur to reduce it, and you could have some microbes. Now, volcanoes, you might say that's most likely, right? But there's no volcano anywhere near here, and these are it's not any form that would suggest that it was volcanic. I can't say that for sure that it's not, but it doesn't match that. Organic material is kind of interesting. Microbes are pretty interesting. So even if we don't have all the answers quite yet, those papers are not yet published. Stay tuned. It opens up a lot of really intriguing possibilities, and at the very least, it tells you this is a material that life on Earth would love to have and would use immediately. So it makes this environment a lot more habitable. All right, now let's go to Perseverance. So Perseverance looks very similar to Curiosity, but has a different set of instrument payload, and then also has a different mission. So Perseverance is seeking signs of ancient life on Mars. That's actually the goal. And not only that, this mission is the first part of Mars sample return, so bringing samples back from Mars for the first time. So many of the goals to accomplish this overarching set of goals are the same as Curiosity. So we're looking for these environments capable of supporting microbial life. We're looking for biosignatures, so things that all of the organics, minerals, etc. That would maybe life would have left behind. We're going to be caching samples. So what that means, we're going to sample them, put them in a pile, and wait for another spacecraft to come get them. So these can be some of the most interesting samples that we encounter. And again, we're still preparing for humans to go to Mars by assessing the environment in a new place. So, okay, here's the same map again. You can see that Jezero, where Perseverance is right over there. And you're going to be like, oh my gosh, they can go on a road trip and visit. This is the width of the United States right here, the Valles Marineris. No, we're not. We're going to wave our little rover arms at each other and never see each other again. It is what it is. But yeah, so just to get, no road trips. Okay, so let me tell you a little bit more about Mars sample return. As I said, Perseverance is the first of this 3-part mission to bring samples back. I have a star here by 2033, and you might have seen the news yesterday. The pass-back budget cancels MSR, but I'm going to remain optimistic. Call your senators. Call Martin. Call Ben Ray. Tell them you want some Mars rocks. We'll see what happens. So for the rest of this talk, 2033 has a star on it. It's just, holding out hope here. What we're doing now is characterizing those rocks, packaging them up, and getting them ready for a future return to Earth. So this is kind of what it looks like. Actually, I guess I messed up because this usually is a video, but it's fine. This is a drill, and it's doing a core, and then it's putting it into one of these sample tubes. And we have held on to some of these sample tubes, but we've also dropped some off. We actually have a little depot where we've left some of those samples. It's like a contingency. If the rover stops working for some reason, we still have some samples that we can get. So we're in the midst of doing that right now. But another really exciting piece of research that has just come out has nothing to do with the samples necessarily. You may have seen in the news that we have announced that we have found a potential biosignature last July. I have to say, this is one of my favorite headlines from the New York Times. NASA did not say it found life on Mars, but it's very excited about this rock. I feel like that's exactly how I feel about this result. Exactly. So this is a rock called Chayava Falls, and it's so cool. There's so many things we could talk about. I know I only have 3 minutes, so I'm going to try not to talk about it the whole time. First of all, it contains organic molecules, some big ones, and it contains water-formed minerals. But the most exciting thing that it has are these microstructures and textures. I don't know if you can see this, but there are these little, so we call this these little leopard spots, right? You can sort of see there's a red rock here, and then there are these dark rims with these white centers. Now, we actually see stuff on Earth that look just like this. These are reduction spots. Reduction chemistry comes back. So how these can form is that you have sedimentary rocks that will have a little bit of organic material embedded in them. And microbes can actually use that. And they can start nomming away. They can be little microbes, and they will start reducing the iron around themselves, making these little bleached spots. So we observe things that look just like this on Earth. And so even more excitingly, you could see that we have some of these, the chemistry here too, right? We have sulfur and phosphorus that are enriched here. So this is multiple lines of evidence. So is this a sign of ancient life on Mars? I don't know. We're going to have to bring it back. We need to do sample return because, there could be a reason that this is happening without life, abiotically. And that would actually really fundamentally shift our understanding of how these processes work on Earth, too. So studying this rock isn't just about Mars. It's actually helping us to interpret things that we see on our own planet. So I'm going to end here. I really believe that once we get these samples back from Mars, it's going to change everything. So let's review. Remember, we know that Mars was habitable when life on Earth already existed. So it's possible if life arose on Earth, it could have arisen on Mars at the same time. We know from all of our measurements that the building blocks of life were there and are still there today. So that means that the idea of ancient life on Mars, it's not crazy. It's actually possible now. This is a real scientific question that we can answer. So as I said, Mars samples will be returned in 2033. So whenever they get here, if it's sooner, if it's later, we are going to be surprised. There are going to be things in there that we have no idea are there. We're going to learn incredible things. And I just, I don't mind waiting for it because I think we'll be able to answer some of those fundamental questions that I outlined before. So I'll leave it there. Thank you.
Okay, do we have any questions for Nina, please?
Very interesting talk. What's the, I guess, operational definition of life that you're all working under? What is not life versus what is life?
There are some really long documents that I can refer you to. It is tricky, right? Because what is the line between organic chemistry and something that's alive? And I think that exact point is still a matter of debate, right? We know that life does a lot of things. And we know when it's leaped over. And that's, I think, so I guess, I don't know exactly. But the line is blurrier, I think, than we realized, which is why I think it's so important that we are looking for these types of chemistries, because it will help us really elucidate where is that line. We don't know that on Earth, and we have all the life around. We could do whatever experiment we want to do, and we still don't know the answer here. So I think that as we start to ask those questions on a planet that seems to be devoid of life, then that's going to help us narrow down that definition on Earth as well. How's that for a non-answer? Sorry about that. Yeah.
Any more questions? Yes. Oh, one here first.
Eileen, I have a question for you. You mentioned stromatolites, and I'm just wondering what the consensus is. Stromatolites on Mars, or are they abiogenic? What is the update with that regarding Mars?
Oh, I'm not sure we've actually definitively found stromatolites, but you're right that we have seen structures that do look stromatolitic. And so that typically that would be something that, again, on Earth forms in a very specific way as they grow toward the sun, right? And they form these domes and they kind of make these layers. We have found sedimentary structures that are, reminiscent, but we haven't been able to study them in detail because typically you would want to be able to like cut that thing in half. And we don't have a saw on the rover, either one of them. So it's hard to say more than these are reminiscent of that type of structure because we aren't able to do the full analysis. Now, what we could do is if we saw one that was big enough and strong enough, we could try to core it and then, bring it back in 2033. That would be, the best way to answer the question, are these actually similar structures or not?
So there's a big
Closer to the mic.
Oh, is this better? Cool. So a lot of there's a lack of atmosphere, and so a lot of UV radiation hits the surface.
There's an atmosphere on Mars, just FYI. Yeah.
Oh, pardon me.
Very thin, very thin.
So there's a lot of thoughts that there's life would be preserved further beneath the surface. With increasing technology and our ability to dig deeper, how do you think that would change our current understanding, and would we potentially find?
I would love to have a drill. And more than what we have now is awesome and all, but it's like 6 centimeters. That's not very deep, right? If we were to do some like really, like oil industry level type of drilling, we would learn a ton. And not just about the potential for life, right? There would be, because the surface radiation environment, as you rightly point out, is terrible, right? We don't expect a lot of organics to be there. And certainly I wouldn't expect any life today to be able to make it at the surface. But I will point out that we still see pretty close to the surface organic molecules preserved. So it's not totally impossible. So I would argue, yes, if we could drill much deeper, we would learn a lot. We would learn a lot more away from this very oxidized surface environment. Let's do it, Yeah, it's just really hard to do with a robot. Send me. We'll go together. Yeah.
Time for one quick question left.
I wanted to ask about returning samples. Is there are already like specific plans or any way that was found to return the samples in a safe and sterile way and examine them?
Yeah, so I actually showed this slide. I mean, this is just like a cartoon, basically, right? I'm like, look, we're gonna do all these things. So 1 is the rover, 2 is a lander that will land, and then it used to have a little fetch rover. We're not gonna do that. The rover Perseverance is gonna put the samples on to the return vehicle, and then it's gonna launch, and it's gonna rendezvous with an orbiting spacecraft, and then put the samples in there, and then those will go back to Earth. And you point out, of course, that you got to make sure that you keep these. They're not going to be sterile, right? We don't want them to be sterilized, but we want them to be kept separate from the Earth environment. So they are put into these sealed canisters already. And then they're going to, then they would land on Earth. They would not, I don't think they would land in the water. They would land on dry land because it would be too precious to accidentally lose it to the ocean, But we would go out to the desert somewhere. We've done this in Utah before. And then we would follow, safety protocols that were established by Apollo sample return because we didn't know what lived on the moon. So like, who even knows? So we've done it before, so we can do this for Mars again. So it's actually quite established. So right, there is a whole architecture and it's planned, but it just got removed from the budget. And we actually need a little money to like buy the spaceship. So yeah, we'll see.
Thank you, Nina,
Yeah,
for a
thank
very
you.
engaging and optimistic talk. Thank you, it's great. I'd like to introduce our next speaker, Dr. Eileen Ryan. Eileen wanted me to tell the students amongst you that the way to prepare for your life is a broad path. She said that she got her master's in physics and then another master's in astronomy and then did a PhD in geology. So she's moved around, and the broader the perspective you get, the better you can choose what excites you, what intrigues you, and therefore what you should pursue. So I'll let her give you some examples of that. Thank you, Eileen.
Hello there. And thanks, Colin, for that introduction. I might add that I'm in the same club as the speakers from this morning, Brian, and also from this afternoon, Nina. I was definitely hooked into science by science fiction. And another fact that will reveal my age is that I was in middle school during the Apollo program. And you can actually go to the gas station and get little paper models that you could put together and build lunar landers and lunar modules and things like that. And so it was an exciting time to be growing up. And Star Trek also, just like Brian, definitely inspired me. And I was quite amazed at, working in this field at NASA. I have not yet met a senior scientist, a program director, or any of the senior administration who doesn't have that same story as Nina, Brian, and I. They were all science fiction nuts who were just grown-up nerds to now focus on real-life science. So what I'm going to talk to you about this afternoon is the work that myself and my fellow astronomer, Bill Ryan, are doing at the Magdelena Ridge Observatory in the area of planetary defense with our 2.4 meter telescope. So I love this front page from the Business Insider. That's a website that's a global news website. And it's a recent article where it declared, hey, do you know comets and asteroids can come out of nowhere and strike the Earth? So, yeah, we were kind of aware of that. And why can they do that? Well, there are very well-behaved asteroids that are in between the orbits of Jupiter and Mars, and they stay there. But through collisional interaction and solar diurnal heating and other effects, they get diverted into this region here where you see the red dots. And those red dots are Earth-crossing asteroids. Okay, so the ones that are well-behaved are here, but we have quite a lot of those objects that get diverted to the inner planets. And when we are really worried about that, it's something that we have to address, and Congress, in their wisdom, actually in the early 1990s, developed the program that actually issued a congressional directive to NASA to find 90% of all objects 150 meters or larger that could potentially threaten the Earth by crossing its orbit. So that was the start of the Planetary Defense Program, or what NASA calls Space Guard. And our telescope is located outside Socorro on Magdelena Ridge, and we are one of the largest NASA-funded telescopes, and we've been working in the Planetary Defense Office for the last 17 years in Space Guard, and it's been one of the more interesting 17 years. I would not, as a young child back in the Apollo program, imagine how much fun you can have with this type of science. So what do we have to do to protect ourselves against potentially Earth-threatening objects like this? Well, we need search telescopes, and NASA has a handful of those, and we also need follow-up telescopes. The Magdelena Ridge 2.4 meter is a follow-up telescope. We're located at 10,600 feet, so very high elevation. And we have interesting characteristics because although 95% of our work is for NASA's Planetary Defense Program, we do some work for the Space Force, looking at artificial satellites. So we are very fast tracking and very capable of looking down very far on the horizon, actually negative 2 degrees below horizontal. And so we have a lot of utility for NASA with our large mirror aperture, as well as these very fast slew rates that the telescope can go. But what we do is we follow up or to get orbit information on asteroids that are discovered by the Discovery telescopes. And here's our facility on Magdelena Ridge. And what the ground-based telescopes do that work in this field is try to get a very good orbit prediction so that we can accurately tell whether that orbit is going to be a problem or not, either tomorrow, 10 years from now, or 100 years or more in the future. So here's a graphical representation of NASA's goal in the Space Guard program for identifying these potentially hazardous objects. Here is a function of asteroid size in kilometers, and then this is the estimated number percentage that we have detected. And so for the largest things, we feel we have reached a good percentage, 100%. These would be termed anything bigger than about a kilometer in size are global killers right here. And we have an indication here of the impact that happened 65 million years ago that wiped out 85% of life on Earth, including all the dinosaurs. That's the Chicxulub impact crater. And that was a 10-kilometer impactor. But you might notice that we don't know a lot of objects that are in this size range. We're still working on that. So more funding, as someone else mentioned, yeah. So here's a more pictorial representation of that. So we're pretty confident the world's not going to end tomorrow because we've got this down. And even we could say 90% is a pretty good estimate. Of course, now that I said that out loud, the cosmos is going to reward me with a killer global impact in the next 10 years from the sunward direction or someplace we can't see on Earth. But we have real concerns about objects that are in this size range. We have like 40% or so identified. So we'd like to get the smaller size objects. And so like this might be, civilization killing, like the Chicxulub impact crater. This is probably more like continent killing. And then here in this range, it's like city killing. So that's just to give you an idea. And to prove to you I'm not making this up about asteroids and comets can come out of nowhere at any time. Here is a map of the impact craters on the surface of the Earth. And some of you might have noticed all those craters on the moon. And gosh, but we're in close proximity to the moon. So so I think you can deduce without being, Sherlock Holmes, that we probably suffered the same impact history here on Earth that the moon did, except that we have a very dynamic surface with lots of resurfacing due to erosion, wind, volcanism, that kind of thing. So it's been a race. But here's the impact craters that have been very well studied on the land portions of our Earth. But as someone else pointed out, we're 70% water. So you can imagine there's a lot more craters buried under there. And of course, this is the image of that Chicxulub dinosaur killing impactor. But I can see sad faces out there for the dinosaurs, right? Don't worry, there's a silver lining, because with the death of the dinosaurs, that allowed mammals to evolve and become preeminent on the surface of the Earth. And so guess what we are? So yeah, poor dinosaurs, but yay humans. But what are we going to do about the fact that they passed the torch to us? Well, let's see. So further evidence that we have, really been bombarded. These are airbursts airburst events. We call them bolide events. They're monitored in the United States and Canada and all over the world. And these dots represent asteroids that have come to the Earth but are too small or made out of a very weak material, and they airburst instead of hitting the Earth's surface. And this is a famous one from not too long ago on February 15th. The Chelyabinsk meteorite exploded over the city of Chelyabinsk, which just to make you think that the universe is kind of has a sense of humor. Chelyabinsk was a city that was used during the war for nuclear munitions factories. And so this is an actual picture about commuting time in Russia. This is the fireball that people saw as they were driving to work, and there were hundreds and hundreds of these video frames that scientists later could analyze. And so the one thing was very good, that through the Space Guard program, NASA has also an international committee of scientists called IWAN, which is run through the UN. And we keep an international group appraised of things. So thank goodness someone didn't think the United States was targeting this city as a potential munitions, active munitions factory, and actually press the nuclear button for the United States to be similarly impacted. But no. But a fun fact is that when people who were driving that morning and they had, where do all these videos come from? Well, I guess there's a lot of insurance fraud in Russia. And so everybody has dash cams on their in their cars. So there was like hundreds and hundreds and hundreds of things to analyze. But it sent this airburst sent 1,500 people to the hospital because the pressure wave was so strong. It ripped off roofs and shattered windows. So it was a significant event. And when we think about that, how can we study is what scientists think. But NASA in the back of their head is like, well, how can we stop this in the future? So the next few slides will address that. We also have evidence of objects, not just airbursting, but these are things that have passed through the geosynchronous satellite belt. So they haven't hit anything yet, but I sure would be sad if my Dish Network satellite were to lose reception on any given night. Here's another impactor. Very recently, an airburst over Indonesia, off the coast of Indonesia. And we took a picture of it about, just a few hours, 10 or 12 hours before it was going to impact. And so NASA's Space Guard program is actually pretty good at discovering these objects, having people get additional data like our follow-up telescope to get a better defined orbit, and then predicting exactly when and where the object is going to hit. We're really close, very, very much on target with time and place of impact. So the work we're doing is very, very accurate. We also have had in the news a close approaching asteroid Apophis, which there are still doomsday predictions that we're going to have it hit the Earth in 2036, but our telescope facility was instrumental, along with a telescope from the University of Hawaii, by reducing the risk that this object would hit the Earth in 2036. And more recently, and this was a gift from the universe in this time of government funding upheaval. This happened in the January, February, March timeframe, where we had asteroid 2024 YR4 was the most dangerous asteroid discovered to date. And it was 63 meters in diameter, so it's smaller than a city killer, but still kind of scary. And this was its orbit. And so when it was discovered, the impact risk was really, really high. And so for NASA, we followed it through till the limiting magnitude for our facility was 25.5 visual magnitude for this object. So we followed it from sometime in mid-January through March 1st. And we reduced the risk to almost 0 to the Earth, together with a bunch of other observatories who took data on this. But the cool thing is that this particular picture of ours that we took was featured on 160 unique news outlets across the world, because this, being the director of the facility, that my job is to do, PR as well as the science. And so I sent this to NASA in case they needed it for anything. Then we took it in January, and that's the asteroid. And I guess they needed it because it was everywhere. It was the New York Times, the Washington Post, CNN, anywhere that you could look. That was the picture that was shown. And just to scare you even more at this halfway point, we're not only worried about objects that have escaped the main asteroid belt and have gone into Earth-crossing orbits, but we also found objects that are from outside of our solar system. So we tracked Oumuamua, and we tracked it through till it was about visual magnitude 24. And we were able to get enough information on its outbound trajectory for the JPL scientists to determine a very accurate potential orbit. It came from out of the solar system because the orbit was not elliptical, it was hyperbolic. It came in, captured by the sun, and then went back out again. So we think it was from Proxima Centauri, our closest star. But yeah, so there's in our solar system and now outside of our solar system, we've got problems. So this is the question NASA is worried about most. Well, so what are we going to do about it? Like, what's your plans? And so, yeah, a lot of times it's shelter in place. Not a comforting option, is it? Evacuation. Or there are, if we have enough time and warning, now a lot of times the smaller guys, the guys that are smaller than 100 meters, we don't have a whole lot of warning. We find them, they're tiny, they're faint, and you basically just have to, either evacuate or duck and cover. But the ones that we are larger tend to give us more lead time. So with those objects, we have some time for planning. So there are several potential ways that we could actually push or deflect an asteroid, not have it come towards the Earth. So we start with just, again, a FEMA-based exercise where we would not have to worry about anything except getting out of the way. And then, or there's a gravity tractor, and then kinetic impactor, and then a standoff nuclear option where we would actually blow up something in close proximity to an asteroid, and the neutrons would blast off some material from the surface and change its orbit. So as this slide points out, the first priority is to test the easiest thing to do. So that's what NASA did. The double asteroid redirect test was launched and impacted a binary asteroid with the small moon Dimorphos with the main parent body Didymos on September 26, 2022 in an attempt to change its orbit, just as the first test of the planetary defense system that NASA had established and has been working on since the 1990s. So we were one of the 4 funded team members to work on this mission, and we were participating scientists. And what DART was designed to do was send the spacecraft itself, which was a vending machine or refrigerator-sized spacecraft, impact it into the small moon Dimorphos, and then see if we could change the orbit of this object. So this is a particularly great experiment for ground-based telescopes because it's a binary asteroid, and we can observe this very detailed through very detailed methods with our ground-based telescopes just by watching the light and the changing light over the evolution of the orbit of Dimorphos around Didymos. And so then we do that, get a change pre and post impact in the orbit, and then measure what was the push that we delivered. So NASA was very excited to stress it's not a movie. We're actually doing this. We're actually going to hit something and try to move it out of the way. And a less dramatic way than Armageddon, Deep Impact, or Don't Look Up. But it's really similar. We're just giving it a shot. So just to give you some appreciation for scale, here's the DART spacecraft. And it's kind of like maybe the diameter, the length of the Statue of Liberty. I'm sorry, the DART spacecraft is refrigerator size. The asteroid that we're trying to hit, Dimorphos, the little moon, is about the size of the Statue of Liberty or a Great Pyramid in volume. And then this parent body, Didymos, is much larger. And these are Earth-crossing objects, so they're very close, but they're not hazardous as of yet. So here's a series of pictures as the spacecraft DART is making its way to the binary asteroid pair. So 90,000 kilometers out, we really don't see anything. Then we start to see a little tiny dot, 25,000 kilometers. And then 920 kilometers, the pair come into view. And then at 12 kilometers, just before the poor spacecraft gave its life to help protect us mammals here on Earth, it sent back this last picture 2 seconds before impact, and that's what it saw. It's a beautiful high-resolution picture of its tragic journey to this object to help out humanity. So it was just a very weird thing to see the poor spacecraft so happy, sending back pictures, and everybody getting really, really excited, and then it was no more. So here's a schematic of what I'm going to show you is the orbit. We had a very good ground-based measurements of Dimorphos's orbit around its parent body, Didymos. Pre-impact, the white line. And then post-impact, this is, okay, spoiler alert. This is what happened. We changed its orbit to an orbit that was closer in to Didymos. And so this guy hit this guy, slowed it down, and Kepler's laws had it go down from reduced energy around Didymos, that it now had a closer orbit and is moving faster, going around the circumference of its orbit. So one of the things that we were trying to figure out for the mission was, okay, so you can remember back to the students in the class, the basic inelastic collisions, right? Two bodies hit each other and they stick, right? So what happens when that happens in this particular case, we're dealing with an actual rock, so we're going to probably make a crater with some ejecta. And that ejecta is going to play a huge role in whether or not we get a big deflection of the asteroid orbit or a little deflection. And so here is where we would assume that there's very little deflection. Here we have some debris happening, and then here we have a lot more heavy ejecta being excreted from the asteroid surface via this crater. So here's a picture of what actually happened. Our telescope took these pictures 10 hours after impact. It wasn't visible in the northern hemisphere until then, and then 34 hours and 58 hours. And I guess we kind of made a mess of this poor little moon, because it looks like there's a lot of ejecta that got created. Here's a picture of this is the first pictures on each of the continents on the world that different facilities took and contributed to this the DART spacecraft project. So that's kind of cool. And here's a schematic of exactly what we did post-impact to try and understand what happened. So here is Earth and then the sun. So you can see as an asteroid rotates, just not a binary pair, but just a single asteroid, it's going to have a a lot of light, then a little bit of light, a lot of light, and a little bit of light, and we get what's called a light curve. So we can tell that to very high accuracy when one rotation of an asteroid. So that's a spin rate. The same could be done for a binary pair where the object goes in front, so you get higher light, or the object goes in back, so you get less light, and it's the same thing repeat. So ground-based telescopes had to measure extremely accurately, and so the team of telescopes working on this produced these light curves. So time and then light intensity here. These are the curves that we got from MRO in just 2 sample periods. We actually observed the asteroid for months. So that was fun, and it's a beautiful picture of our facility. But the great, amazing result with all that ejecta, so it was completely within what it's expected from physics, was that we made the orbit faster by 32 minutes. Now, we would have thought it was a success if we had just done like 7 minutes or something like that, but 32 minutes, and that is because what we did by creating all of that ejecta, it was like an extra impulse to the system, and the parameter that we used to assess that above the basic physics of inelastic collisions is that by creating ejecta, in this particular case with this particular geology of Dimorphos, we were able to enhance the kinetic energy impact of Dimorphos by 3.6 times what it would have been if it didn't produce the ejecta. So that is good, because most asteroids are kind of fluffy balls of dust and have been, hit with collisions in their past, and they're continually reaccreting and evolving. So it's good that most of them will be of this composition. So maybe if we had to worry about it, this would be a great first test of a kinetic impactor. And so the work was featured in a special issue of Nature, where we were able to report that NASA had its first successful test of the Planetary Defense System, where we could use a harmless, poor spacecraft to impact an asteroid at 6.3 kilometers per second and cause this type of deflection. So, yeah, rest assured you won't have any nightmares tonight, because we're on the case. So the trick is finding them, so we still have to have an ongoing program trying to find these objects. So any given night when Bill and I are operating the telescope, there might be 25 or more new asteroids discovered. And so we, together with just a handful of other telescopes, have to follow up and get an orbit for these objects, because, all of the asteroids are still going around the sun. They're in orbit around the sun. So Discovery has only a tiny portion of that elliptical orbit that it has defined. So a follow-up telescope will extend the arc of the orbit so that we can very carefully draw exactly what that asteroid is going to do and when. So that will tell us whether it's potentially hazardous. And just to not scare you, but there are about 7,000 or 8,000 asteroids currently known by NASA that could be potentially hazardous in the future. That's not too bad, right? 8,000? That's not bad. So to conclude, the dinosaurs passed the torch such that they could not stop the Chicxulub impact crater from happening. But perhaps if we humans work really, really hard and develop our technology and do maybe additional tests of kinetic impactors, or maybe in the future gravity tractors, or even a standoff nuclear explosion, then we can escape the fate of the dinosaurs. So thank you.
Thank you very much, Eileen. Maybe this is another example of evolution. The dinosaurs couldn't make it, but their evolution has led to some species that maybe can. We'll see.
We'll
we
see
don't
if there's
kill
funding
ourselves
cuts.
first.
Yeah.
Other questions?
Thank you for the great presentation. Can you go more into the gravity tractor and what that might be, or if it already exists, what it
Well,
is?
that one, I'm not a specialist in the mitigation techniques, but the gravity tractor is a big favorite amongst NASA administrators because it's very low key, but it does require a lot of time. So you have a spacecraft, it kind of like a tractor beam on Star Trek, you know, it goes close to that object, and over time, pulls it just tiny bits at a time. And that is what pushes it out of the way instead of our poor DART spacecraft. I mean, I should let you know that the European Space Agency had launched Hera, which is a follow-up space craft program which will assume orbit around the Didymos-Dimorphos pair. And it was launched in October 2024, and I think it's going to take 2 years to get there. And so it actually will give us pictures of the crater that was made from our DART impact, since, well, we all know DART was in no condition to take pictures. So
this is a question about early warning. So you showed, for example, the Chelyabinsk event, and you saw it about 12 hours before it occurred. Did you?
it was not, Chelyabinsk came from a sunward direction.
Okay.
So that is a really important question. And so NASA has been working for, I would say, the last 15 years in launching a space-based telescope that will not be as affected by objects coming from the sunward direction. There is a high percentage, or enough of a percentage of objects coming from there and have caught us unaware. So they will be, NEO Surveyor will be launched, hopefully, again, pending any budget cuts, but that is ready to go, and that will be looking from space in the infrared, and so that will be less subject to being hidden by the sun. So Chelyabinsk was hidden. The one I had showed you, we had 12 hours warning, was over the Philippines. It was just off the coast of the Philippines, but it was a much smaller guy. So we usually can find the city killers, but this one was, I'm trying to remember, but it was less than 10 meters. So it was something that, you know, harmlessly airburst off the coast of the Philippines, but it was a pretty fireball. So
But yeah, so I did remember that Chelyabinsk seemed to catch everyone by surprise.
it did, yeah.
And then I thought you said you had the 12 hours of warning, and I thought, well, why didn't you call somebody?
I know, right?
So
but again, most of the people in Russia, when surveyed post Chelyabinsk, they were asked to pick on a survey question, what did they think that was? Some picked nuclear bomb or a missile. Some picked, very few picked asteroid or meteorite. Most people picked alien spacecraft. I would think it was the percentage was 65% of the Russian population of Chelyabinsk believed it was an alien spacecraft re-entering the Earth's atmosphere.
Hi, I had a question about how you figured how the percentage of the discovered asteroids was found.
That's an excellent question. It's not based on anything real, right? Because we can't go up there and count them. So it's numerical simulations based on the evolution and the mass estimate for the material that's up there, and exactly how in the early solar system a planet failed to accrete between the orbits of Mars and Jupiter. So it's all numerical simulations for our solar system formation that give us an estimate of the mass. So that estimate continues to change. And I'm wondering whether, you know, it will improve any more than we have it currently, but it's based on a mass estimate for what should be out there and what percentage of that we found, based on a power law size distribution, because we think, you know, we know exactly how, and it's confirmed with the larger objects that we have found, that it's a power law distribution with size, and so it gets, less numerous for the bigger objects and more numerous for the smaller ones.
Okay, well, thank you very much, Eileen, for another engaging presentation. But unlike Nina's optimistic presentation, this one's more a sort of a fingers crossed.
Actually, Colin, I wanted to make a comment, not a question, but you know, as Eileen and Bill know, I've been interested in this subject for a very long time, and I have to say that, you know, when the DART impact was about to happen, we, you know, my family was watching the videos and all that sort of thing. My 3-year-old granddaughter was absolutely fascinated by it and asked to watch it again and again and again. And, you know, I'm hoping that she will be inspired to do some of the same work. And the other thing is, how can we not have a sleepless night tonight, since knowing that you and Bill are both here?
Good question. Yeah. I mean, I'm not exaggerating when I'm saying that the Planetary Defense Office is basically, I mean, someone once said it's like not much larger than the staff required to run a McDonald's restaurant. I mean, so there's like 3 Discovery telescopes, 5 follow-up telescopes, a lot of amateur astronomers who contribute very valuably to follow up, you know, finding these objects and extending the orbit. But rest assured that we have, even though the observatory is 17 years old, we have complete ability to work remotely. And Bill is ready at any time while I'm here at this conference. He's with me today after sleeping the morning to get on the internet from our hotel and do observations. We have taken observations all over the world, Australia, Tahiti, Italy, everywhere, and oftentimes from Holiday Inn Expresses. So, yeah.
Okay, 15-minute break. We come back at 3 o'clock.
Yeah, you got 24, maybe 48